Physical geology class, this is chapter 12, the Earth's interior. The Earth can be divided up into three major shells or layers in its interior. Okay, and those three major layers can be further divided into separate zones. We'll talk about those reasons, but the three basic divisions are kind of distinguished by the chemical differences between them. Okay, gravity and chemistry allow for those changes. So essentially, the heaviest material sank towards the center of the Earth. That's the densest material, or iron and nickel. The least dense material makes up the outer layers, like the crust and mantle. Okay, and then those layers have small horizontal variations in mineral composition with changing temperature and depth. Okay, and so these small differences is what makes the Earth's interior very dynamic. So here, for example, on the left-hand side, here's the division in terms of chemistry, right? We've got the crust, which is made up of the least dense material on the most outer portion of the Earth, 5 to 70 kilometers thick, right around ocean crust, and this is the thickest continental crust. Below that, we have the mantle. This makes up the majority of the Earth, about 88%. Okay, and this is made up of silicate rocks that have a lot of iron and magnesium. The crust is made up of silicate rocks with a lot of potassium, silica, calcium, sodium. Okay, much lighter silicate rocks. These are kind of heavier silicate rocks that make up the mantle, peridotite. Okay, and then the core, and the core is made up of iron and nickel, the densest and heaviest stuff. So this is based on chemistry on this left side. On the right side, these layers of the Earth are segregated based on how the material behaves. Okay, so we'll have the lithosphere, which is the crust and uppermost portion of the mantle. Then we have the asthenosphere. Then we have the lower mantle. Okay, outer core, which is liquid, and inner core, which is solid. Okay, so the lithosphere is here. You can see that includes ocean crust and continental crust with a portion of the lithospheric mantle, so here and here. So this here would be the lithosphere, and this here would be the lithosphere. Now the lithosphere gets its designation because it's strong and it's brittle. Okay, so it's based on its behavior. So this material breaks. This is where earthquakes are generated and all that. Below the lithosphere is the asthenosphere. Now the asthenosphere are made up of primarily mantle rocks, mostly mantle rocks, and they're very close to their melting temperatures, so they're really hot, and they're very close, because they're very close to their melting temperatures, they're very weak, and that allows them to flow plastically. It's still a solid, but it's able to flow plastically and move. So that's the distinction here with this arrow up here. That's the lithosphere and asthenosphere. Once you go beyond the asthenosphere in the lower mantle, this is really hot, but because the pressure is so great and has increased because you're going deeper and deeper within the Earth, this stuff behaves rigidly again in the lower mantle. Okay, so what we see that changes as you go deeper and deeper within the Earth are mineral changes and phase changes. Essentially what happens is minerals have stability limits. They're only stable under certain temperatures and pressures, and when you exceed those temperatures and pressures, those minerals will undergo a change. They'll change their structure and become new minerals that can withstand the new environment, the higher pressures and higher temperatures. So the density of rocks as you go from the surface towards the center of the Earth increases because of gravity. So that pulls down the heavier material closer to the center of the Earth. Upper mantle rocks have a density of 3.3 grams per cubic centimeter, and the same peridotites, the same rocks in the lower mantle, have an increased density of 5.6 per centimeters cubed, so grams per centimeters cubed. So that just, the increased pressure kind of compresses these rocks and increases their density. So the peridotite in the lower mantle, what happens there is they undergo mineral phase changes because those minerals are so compressed due to the high pressures. Okay, so the reason why we know so much about the Earth's interior is because of seismic waves. Seismic waves that can propagate through the interior of the Earth. Okay, so seismologists have really broken down in conjunction with petrologists. Petrologists are geologists that study minerals. So they do various experiments with minerals to test their stability limits and pressures and temperatures to find out what phase changes occur. And through that collaboration, seismologists and petrologists have been able to kind of narrow down and get a good idea of what the Earth's interior is. Excuse me. And seismologists, they understand the interior of the Earth through indirect data or looking at seismic velocities or seismic waves traveling through the interior of the Earth. And as they pass through different materials of the interior of the Earth, their velocities change and they vary. Okay, so the travel times of primary waves or compressional waves and shear waves, they vary depending on the material they move through, the properties of that material. So a general rule is seismic waves will travel faster through stiff and rigid rocks, okay? And seismic wave velocities will also vary based on the composition of those rocks. Okay, so here you go. If you have an earthquake, here are the wave fronts that travel and propagate in 3 dimensions through the entire Earth's interior. And their velocities change as they go deeper and deeper within the Earth. Okay, so these are the paths that the wave fronts take. This is how we, quote unquote, see into the interior of our planet. Okay. Seismic waves also reflect and refract as they pass through different layers of the Earth. This also gives us information about those layers. P and S waves, as we already know, they travel at different velocities. So depending on the properties of the material they transmit through them, their velocities will go up and down. The velocities of these seismic waves increase through more rigid materials. And an interesting property of secondary waves is that they cannot travel through liquids. So as primary and secondary waves move or propagate through the Earth's crust and mantle and into and towards the core, some waves will just get reflected directly away. Okay, some waves will get refracted and slow down as they pass through a different material. This is the outer liquid core. So you would see a decrease in velocity here. So here are some diffracted waves. Okay, so here's an example of what would happen as seismic waves travel through 2 different rock types. Okay, so when a seismic wave encounters a boundary between 2 materials or 2 different rock types, and it can even be air and water or even rock and air as an example. Primary waves can do that. They'll either be reflected or refracted. Okay, so here comes a seismic wave, and this is, if it comes in at the right angle, it can be reflected from the material. Or it can be refracted, meaning that its velocity will change as it passes through the new material. Okay, seismic velocities can increase. If you have a seismic wave moving through rock type 1 and it's not as hard or brittle or dense as rock type 2, as soon as it travels into rock type 2, its velocity will increase, and so it kind of bends upwards in this direction, refracts this way. Okay, but if rock 1 is like denser and more rigid, maybe rock type 2 is a little hotter, so it's a little less dense or something, less rigid. The seismic wave will slow down, and if the seismic wave slows down, it bends in the opposite direction. It kind of bends downwards like that. So it refracts. Okay, so these ray paths, bending ray paths, are the result of the increase and decrease of seismic wave velocity as they're traveling through different layers of the interior of the Earth. Okay, so by studying the seismic waves traveling through the interior of the Earth, that gives us an understanding of what the Earth's composition is. We can run experiments and find out what the seismic wave velocities should be like at different temperatures and pressures using different experimental tools. Petrologists, a lot of them have these where they're big anvils where they can like crush materials. And so we can kind of get an understanding of how fast different seismic waves can move through different materials. Okay, so if we look at that behavior of rocks and different pressures at various depths, it can give us an idea of what the composition of the different layers and the changes that are occurring in these different layers. Okay, so here's a really cool example. Here's the surface of the Earth. Here are all the layers, the different layers, right? Here's the lithosphere to scale, so it's very thin as compared to everything else. Here's the asthenosphere. Okay, this is the transition zone. We'll talk about that in a second. Here's the lower mantle. Okay, here's the liquid outer core, and here's the solid inner core. Okay, here on the x-axis is the velocity of these seismic waves. On the y-axis is depth. Okay, and so here are S waves, and here are P waves. Okay, so as primary waves kind of move through the interior of the Earth, if you notice, their velocities gradually increase, okay, in the lithosphere. So the deeper you go, the faster the velocities are, and that makes sense because the pressure is increasing, and when the pressure increases, it makes the rocks a little more dense, and then the seismic velocities can be faster. But then if you notice, it kind of stalls, like the velocities kind of are constant right here, and they kind of maybe jump back a little bit. We call that a discontinuity, where the seismic velocities actually don't increase, they might decrease a little bit, and then they start increasing all over again. And the reason for that change, right around 100 kilometers on average, is because we're transitioning from the lithosphere to the asthenosphere. Remember, the asthenosphere is made up of mantle rocks that are close to their melting temperatures, so they're really hot and they're kind of plastic. Well, that will slow down the seismic velocities, and that's why we see that discontinuity right there. Sorry, let me erase that. Okay, and then as you're in the asthenosphere, you start to increase in those seismic velocities until you see a huge increase right here. Okay, this is the beginning of what we refer to as the transition zone. We see a big jump in seismic velocities from here to here, and the reason is there's a mineral phase change right around 410 kilometers. That's when you're kind of transitioning to, this is no longer the asthenosphere, this is a rigid mantle, okay, and new minerals that are stable at depths of about 410 kilometers are showing up here, and that's why you see the jump in velocities. And again, there's a stable increase in velocities, in P-wave velocities, and then there's another jump right around here once you get to the lower mantle, another discontinuity, another jump in velocities, because at about 660, seismologists saw that there's another discontinuity and a jump in seismic velocities. And so seismologists conveyed that information to petrologists, and petrologists experimentally determined that there are certain minerals in peridotite in the mantle that will undergo that phase change into a new mineral at approximately those depths. So they put those two things together, and that's the reason for that increase in P-wave velocities. Then in the lower mantle, the P-wave velocities increase with depth, as you would expect as pressure increases. But then look at this discontinuity. The seismic velocities abruptly decrease all the way over here, right around, let's say, 2,800 kilometers of depth. And that's because the seismic waves have encountered the core of the Earth. Okay, and in the core of the Earth, we know that this is a liquid, okay, the outer core. The reason why we know this is a liquid, S waves kind of mimic everything that's happening with the P waves, same results with the discontinuities in the different layers, but S waves cannot travel through liquids, and so they abruptly end at the liquid outer core, and they can no longer travel through a liquid. That's how we know the liquid outer core, or the outer core, is liquid because of that, in addition to the P-wave velocities dropping drastically. Okay, and then the P-wave velocities increase steadily as you go deeper and deeper because of the increase in pressure. Then there's the next discontinuity, and seismic wave velocities abruptly jump up, okay, and then they increase, okay, and that discontinuity indicates to us that the inner core is solid, okay. So that's how we know. Okay, so here are the Earth's layers, just to reiterate after going through all that information. We've got the Earth's crust, which can be either made up of ocean crust or continental crust. Ocean crust has a density of 3.0 grams per cubic centimeter. Okay, a little denser than the continental crust, which is 2.7. That's why the ocean crust subducts into the mantle when they collide in a convergent plate boundary with the continental crust. Okay, so ocean crust, as you know, it forms at mid-ocean ridges. It's very thin in comparison to continental crust, only 7 kilometers, and it's composed of basalt, upper layers of basalt, the volcanic rock, and then the intrusive equivalent of basalt, which is gabbro. Okay, the continental crust, it varies in its composition because you can have igneous, sedimentary, or metamorphic rocks that make up the continental crust. Its structure and composition, its structure is different everywhere because of plate tectonics. The average thickness is about 40 kilometers, okay? But in its thickest areas, like in the Himalayas or the Peruvian Andes, it's about 70 kilometers thick. In the thinnest areas, the Basin and Range province, which is essentially the entire state of Nevada, that area of the crust is getting stretched out and thinned, and it's only about 20 kilometers there. Okay, below the crust, there's this other layer was discovered by a Croatian seismologist. I can't pronounce his last name, but it starts with Moho. So this layer bears his name. It's essentially the Moho is the boundary between the crust and the mantle. Okay, and what they discovered in 1909 were that P waves below the base of continents, velocities abruptly increase right at the Moho. Okay. And a lot of seismic waves refract as they cross the Moho. Okay, so here's kind of like that, a little experiment. There's an earthquake in the crust. We've got 3 seismic stations, okay? And the direct kind of P waves or seismic waves that are traveling and making the ground shake as they travel to each one of the seismic station, these are the direct waves. So they're just kind of going from the earthquake propagating outwards, right? But other, see, the wavefronts are moving like this, and other wavefronts, the same wavefront will strike the Moho, the boundary between crust and mantle. So this would be crust, and this is the mantle. It encounters the Moho, and the velocities abruptly increase. So this seismic wave is traveling at a faster velocity. And in fact, what will happen is that it'll refract and then hit seismic station number 3 and arrive there before the direct seismic wave. And that's what had perplexed these seismologists initially until they discovered that there was this Moho layer. Okay, then below the Moho formally begins the mantle. The mantle is, I'm sorry, I guess I misspoke, 82% of the mantle. I think I said 88 earlier, so 82% of the mantle. Okay, about 2,900 thick. Kilometers thick and extends from the Moho to the liquid outer core. Okay, it's made up of silicate. It's a silicate rock. Okay, and it's silicate rocks that are rich in iron and magnesium. Okay, lots of olivine, lots of pyroxenes. Okay, the kind of dark silicates. Okay, and this is we've determined. Well, one is that we do get volcanic eruptions that carry portions of the mantle to the surface, and then another way is we confirm it with the observations of seismic waves. Okay, the upper mantle, which is the from the Moho to about 660 kilometers, that's composed of peridotite, that green rock with a lot of olivine in it. Okay, this is also referred to as the lithospheric mantle. The lithospheric mantle is the upper portion of the mantle, okay, the uppermost part, and that's the part that behaves rigidly. Okay, it ranges in thickness, and it can go up to about a depth of 200 kilometers. The lithospheric mantle and the crust is what makes up the lithosphere, so the tectonic plates. So underneath this, then you'd find the asthenosphere. Okay. This is the weak layer beneath the lithospheric mantle. This is what allows lithospheric plates to kind of float on top of the asthenosphere. Okay. Below the asthenosphere, beginning at about 410 kilometers to about a depth of 660 kilometers, we refer to this as a transition zone. It's a transition zone because there are specific mineral changes. Because of the increase in pressure, olivine begins to convert into a new mineral called spinel. Okay, pyroxene then converts into a new structure. This is a phase change. It's the same mineral, just a different structure to withstand the higher pressures. And it kind of has a similar garnet-like structure. Okay, so those changes occur at about 410 and 660 kilometers. Then beyond 660 kilometers, this is considered the lower mantle. It's the Earth's largest layer, about 56% of the Earth's volume. And here, beyond 660, there's another mineral change. Olivine and pyroxene are converted to a new mineral called perovskite. Okay. Then there's a layer in between the lower mantle and the outer core. We call it the D double prime layer. Okay, and it's we believe to be highly variable material. It's silicate material, rock material, and it's kind of like the boundary between the outer core and the lower mantle. And a lot of seismic studies have shown that the temperature varies in different portions of the double D layer, and some scientists believe that this is the graveyard of subducted ocean lithosphere, that it'll make it all the way to the core mantle boundary, and this is like the graveyard for subducted plates. Okay, and the really hot regions are thought to be areas that become displaced from these subducted ocean plates, and they rise, and that becomes the hotspots we know of today, like the hotspot beneath Hawaii, or a hotspot beneath the Galapagos Islands, or Reunion. Okay. So how did we discover the core mantle boundary? Well, what happened was when seismologists were studying seismic waves kind of traveling through the interior of the Earth, they found out that if an earthquake occurred on one side of the Earth, on the other side there'd be something called a shadow zone, and they wouldn't receive any S waves. And P waves are considerably refracted through liquid. And so say there's an earthquake over here, here are the wave fronts and the direct paths of P waves. Okay, they get slowed down by the outer core here. Of course, back then they didn't know it was an outer core. This is how they determined it. And then they noticed that there was no S waves. And so an entire portion of the Earth, if you had seismic stations over here, you would get no readings. This would be the P wave shadow zone. Okay, so this is for P waves. For S waves, the shadow zone is much larger. It'd be basically this entire area here. So like this area here, people would receive P waves but no S waves. Right? But then all here you wouldn't receive any S waves. So that's really how they determined that the outer core is liquid, essentially. Okay, the outer core has a density of about 9.9 grams per cubic centimeter. Okay, it's mostly iron with some nickel. 15% of the outer cores consist of lighter elements. I guess we're not entirely sure what that is. They could think it's sulfur or carbon. And the core, outer core and inner core makes up about 1/6 of the Earth's volume. Okay. The inner core solid has the highest density, 13 grams per cubic centimeter, and the Earth is slowly cooling down. And as it cools down, the outer core is essentially crystallizing and settling and allowing the inner core to grow. So the inner core kind of grows at the expense of the outer core. The inner core also rotates faster and moves independently of the crust and the mantle and the rotation of the Earth, which is kind of interesting. And if you think about it, the inner core is the only actual solid sphere, right? Because there's everything else that surrounds it, the liquid outer core, the mantle, and the crust, they're all shells that surround the inner core. So it's almost like a planet within the planet. No. So yeah, let's see. Here we go. This is the solid inner core. It rotates independently of the Earth's rotation. And the reason why we know it rotates is because the fastest route for seismic waves is shifting and turning eastward. So over the past 96 years of collecting seismic data, we've noticed that the path for the fastest seismic waves are changing or moving eastward, and that indicates that the solid inner core is rotating. Okay, so how does, what's the deal with Earth's temperature as we move through the different layers? Heat kind of either conducts or convects through the different layers of the Earth, and it goes from the interior of the Earth outward. Okay, the core is really hot. It's estimated to be about 5,500 degrees Celsius, and the Earth's surface is only 15 degrees Celsius. Okay, so heat flows from the core to the surface. We have the highest heat flow at mid-ocean ridges and the lowest heat flow at abyssal plains. Let me show you a picture of that. So here are all the mid-ocean ridges, and anywhere that's in red or orange or yellow, that's high heat flow. And that makes sense because this is where new ocean crust is being generated, and there are a lot of, it's associated with a lot of volcanic activity, and the mantle's kind of upwelling or kind of rising and decompressing in those areas, so it's very close to the surface, and therefore it's very hot. Okay, continents and abyssal plains are the much cooler areas. See these kind of blue areas because they're the thickest parts of our crust, so they're very cold in comparison. So a good question is, how does our Earth get so hot? How is it so hot, which causes all this mass movement? And the reason is the Earth had kind of early on in its formation had two major thermal stages. The first stage, which lasted only the first 50 million years when Earth first formed, temperatures on our growing planetesimal were rising rapidly because of collisions with other planetesimal. This is the kind of the accretion stage where mass was just kind of accumulating and running into each other. In addition to that, there were a lot of short-lived radioactive isotopes that were just decaying away really quickly. And as they decay away, they release a lot of heat. And so that heated up our planetesimal Earth, which was heterogeneous at the time, and that generated so much heat that it began to melt the material. Okay. Another major event that occurred was the collision that created our moon. Here it says an asteroid collision, but I've also read that it's believed the moon was another small planetesimal that was rotating the sun. Orbiting the sun. Okay, and this caused the temperature increase. Okay, and the second stage is what we're experiencing now, the slow cooling over the next 4.5 billion years. The heat from the center of the Earth is kind of radiating outwards. That's we're on like a slow boil, so to speak. And a lot of that heat is still generated through long-lived radioactive isotopes. So we still have a lot of isotopic systems and elements that aren't stable and are radioactivity decaying at a very slow rate. So that's kind of like the heat that's being generated. That's the slow burner, so to speak. Okay, so here it is. Here is the formation of our Earth as a planetesimal, super hot, caused melting, and that melting caused differentiation. Heavy stuff kind of went down towards the center of the Earth, and light stuff went out to the upper layers. Okay, but then over time, the short-lived isotopes kind of decayed away, and then the long-lived isotopes kind of kept the heat going in the interior of the Earth. Okay, so heat flows through the Earth in three ways: conduction, convection, and radiation. Convection and conduction occur in the Earth's interior, and radiation transports the heat away from the surface of the Earth. Okay, so here the inner core is made up of a solid, so heat travels through a solid, but via conduction. It's kind of like when you heat up, excuse me, you guys can't read anything if I draw too much, but if you heat up like a skillet to cook some food, you're heating up a solid, and that will conduct heat through the metal. Okay, same thing's going on in the inner core. Because the liquid core is, or the outer core is liquid, this will actually convect and conduct. So the liquid core actually moves. There's mass movement, and there's movement of the liquid outer core, so that's how it helps transfer heat. But it's also a metal. It's a liquid metal, so it also conducts heat as well. Okay. When you get to the mantle's got convection currents, kind of like water boiling. Okay, so it creates these huge convection currents, and it has mass flow, and that's where we see convection. And then when you hit the lithosphere, because the lithosphere is solid and it doesn't flow, heat will conduct through the lithosphere and onto the surface of the Earth and radiate outwards into space. Okay, so convection essentially is the transfer of heat where materials replace, hot material replaces cold material, and you create convection currents. That's the primary way heat is transferred through the Earth. Okay, so it's very similar to water boiling. Okay, and what it's dependent on is the viscosity of the material. Okay, if something is very viscous, it won't flow very fast, so heat flows slower. If the material has low viscosity, it can flow faster, so heat increases rapidly. I don't know why I'm drawing arrows. Jeez. Okay. So here, this is the Whole-Mantle Convection model. Okay, so we have here the lithosphere, we have subduction, right? Here is that subducting ocean plates. We have seismic data that suggests that it breaks apart and makes it all the way to the double D layer down here. So we think a bunch of subducted ocean plate makes it into this layer, okay? That displaces a lot of hot lower mantle, which rises, okay? And this creates those hot spots. So these are those convection currents in the mantle that we're talking about. Okay, conduction is essentially just heat traveling through a solid. It's the collision of atoms and the heat, or through the flow of electrons. So different materials conduct heat at different rates. Okay, metals are much better at conducting heat than rocks are, and as an example, diamonds are much better at conducting heat than air. Okay. But it's not a very efficient way of moving heat. So most rocks are very poor conductors of heat. Okay. So conduction is important in the solid inner core, then convection becomes more important in the outer core of the crust. Okay. The crystallization of iron in the liquid outer core is what drives kind of the chemical convection. Okay. And then those radioactive isotopes is what provides the heat for those reactions. Okay, so if we were to look at the Earth's temperature profile, we'd call that the geothermal gradient. And so that's essentially like how much the temperature goes up the deeper and deeper you go within the Earth, okay? And it varies, okay? The crust, if you're in the crust, it's approximately every kilometer of depth you go, the temperature will increase by 30 degrees Celsius. And that's an average. In the mantle, the gradient slows down. So in the mantle, the temperature increase is only 0.3 degrees Celsius per kilometer. So once you're in the mantle, the temperatures kind of stabilize and slowly increase. There is an exception in the D layer. D layer can be hotter or colder depending on what you're looking at. It's variable. Okay. The base of the lithosphere, as a result, this is degrees Celsius. Excuse me, I don't know why that's out of here, but the base of the mantle is about 2,500 degrees Celsius, and the center, the core of the Earth, is 5,500 degrees Celsius. It's pretty hot. Okay, so here, let's not get lost in charts here. Let me break it down for you guys. Let's unpack this. All right, this is the surface of the Earth, okay, and this is depth. So when you go in this direction, you're going deeper and deeper within the Earth. So that's 6,000 kilometers. Each different color is a different layer. So here's the lithosphere, asthenosphere, okay. Here's the lower mantle, okay? Here's the outer core, and here's the inner core, okay? So this is the orange line here is the geothermal gradient, okay? So the geothermal gradient is the temperature increase we see. Remember in the lithosphere, it increases rapidly, 30 degrees per kilometer as you go deeper and deeper, so it gets really hot. Then when you get to the mantle, it kind of levels off, and it doesn't really heat up as quickly as you'd like, okay? And then this blue line over here, it indicates the melting temperatures of the rocks in these layers, right? So here's the melting temperature of the lithosphere. These are the melting temperatures and pressures of the asthenosphere and lower mantle. And if you notice, and we've talked about this before, the lower mantle is solid, and that's because it doesn't get quite hot enough to melt the lower mantle. But these two lines almost intersect right here, and this is typically where melts are generated. And melts are generated because of plate tectonic triggers, right? Like decompression or addition of water, okay? So melting typically occurs right around here, and it can be anywhere between 100 and like 50 kilometers of depth. So that's where the geothermal gradient, it gets hot enough, really close to the melting temperatures of rocks at that specific depth. Okay, but then these two lines diverge from each other. So the lower mantle is solid. So this is solid rock from here to about here. But if you notice, the temperatures increase abruptly right at the outer core, and that's because we're dealing with a different material now. And when you're dealing with a different material, its melting curve also will change. And so here what you see is the geothermal gradient crosses the blue line, and when that means it's hot enough for this material to melt. And therefore, throughout the entire portion of the outer core right here, it's liquid because it's hot enough to melt iron and nickel, and that's why it's a liquid. So this is a liquid, this is a solid, okay? And the reason is because it gets hot enough. It gets hot enough, this material, its melting temperature is lower, and so it melts. And then once you get to the inner core, right around here, those two lines cross again, and now in order to melt iron and nickel at these pressures, at higher pressures, the temperature has to be higher. But the temperature really doesn't reach that high, so therefore the inner core is a solid. Okay. And over here, this just talks about the viscosity of the material. Okay, so the viscosity of the uppermost strong lithosphere is really high, meaning that it doesn't flow, it doesn't move. But with depth, it decreases because temperature is increasing and reaches kind of like a low right at the asthenosphere, right? So right at the base of the lithosphere, we have the least viscous material, the upper asthenosphere, so to speak. So this area is really capable of quicker flow, okay? But then as you go deeper and deeper, the viscosity increases and reaches a maximum when you get to really high depths, and that's because of the increase in pressure. But then it weakens as you get to the D layer, okay? Okay, let's talk about Earth's gravity. Earth's gravity is actually variable depending on where you are. We don't live on a perfect sphere. It's kind of like bulgy around the equator. There's kind of like an equatorial bulge. Or just imagine if you're holding a sphere and you kind of put your hands on the poles and then you squeeze it, and then so that it would push the equator out towards space a little further. It's very slight, but that's the idea. And so the rotation of the Earth causes a centrifugal force at the equator, and that lowers the gravitational force because you're kind of like further away from the center of the Earth, so you feel less gravity, okay? So that Earth shape that I was talking about, that means it's an oblate ellipsoid, so there are bulges at the equator, all right? And other variations of gravity on the Earth can be due to the rocks that are present beneath the surface. If you have bodies of rock that are unusually dense, well, I don't know why I crossed it out, that'll make gravity greater. Okay, and historically that's been used to help find metals and metallic ores because they're heavier. So if you see changes in gravity in a specific area, very slight changes, that might indicate that there are metal ores in the crust. Okay, so let's pretend you're a fisherman at the equator, Peruvian or Ecuadorian fisherman right around here. You weigh about 200 pounds. Okay, the Earth's gravity is greater at the North Pole, so this Inuit, they have the same mass. They're a fisherman of 200 pounds. But if this Inuit moved to Ecuador, they would lose weight because Earth's gravity is less at the equator. So your weight is relative, guys. This is a good weight loss program. Move to the equator of the Earth. There's a little bulged out there, and you'll lose a pound or more. I mean, if you're more massive. Okay, so here are some more smaller differences in gravity, just depending on where you are. Here's a kind of gravity anomaly map of the United States. Okay, anywhere in red, you have higher gravity anomalies than normal, and anywhere in blue, you have lower gravity anomalies. Okay, so the Basin and Range province, this whole area here is very thin crust, okay, only about 20 kilometers. So when you have very thin crust here, that leads to lower gravity anomalies, okay. Wherever you see red here, this was a mid-continent rift or a failed rift, meaning that there's a lot of dense volcanic rocks that about 1 billion years ago that filled up this area and crystallized. So a lot of dense rocks are here, and therefore the gravity here is just a little bit higher than in the surrounding areas. And the reason why mountain chains have lower gravity is because these are old mountain chains that are weathering away and they're uplifting, okay? And those deep roots are made up of less dense rocks, and that's what accounts for the lower gravity in these areas, okay? Just like, and the way they measure that essentially is using a well-calibrated spring, and depending on where you are, if there's higher gravity, it'll pull the spring down further down, and if there's less gravity, it doesn't pull as hard. Okay. Then there's the science of seismic tomography, and this is super interesting because this collects data at different seismic stations to kind of see the interior of the planet. Okay, this is the only data we can directly kind of extract from the interior of the planet to see what's going on. And it gives us three-dimensional pictures or ideas of what's down there. Okay, it identifies regions within the Earth where there's P and S waves travel slower or faster depending on the material moves through. So it helps us identify mantle plumes and subducted plates. Okay. So check this out. This is a cross section. Here are all the seismic stations 1, 2, 3, 4, 5, and then this is the cross section of it. Okay, so here's across North America. Here's the Pacific Ocean 1, 2, 3, 4, 5. Okay, we can see here. This is the remnants of the Farallon plate. Seismic velocities travel faster along these blue areas because this is kind of denser and cold material, and so these are little chunks of the subducted Farallon plate that are sinking towards the mantle. And that's what we think. We think these subducting plates kind of make it all the way to the core mantle boundary and displace this material, and then you have hot material rising as a result of it. Okay, we've identified, this is pretty cool, seismologists have identified a new mantle plume that's forming at the core mantle boundary, and it's directly underneath Africa. Okay, so this thing's most likely going to rise and then rise towards the surface of the Earth. But I mean, who knows? Plate tectonics, maybe Africa will move away in a different direction. And again, this is probably millions of years from now. If you notice here, right at the Mid-Atlantic Ridge, this is where we have upwelling mantle that's melting to create new ocean crust. It's all red because this is all really hot material. When you look at North America, it's mostly blue because these are older portions of the continents. Okay, Africa, very large continent, mostly blue because it's very old. Okay, slow-moving seismic waves. Here's the Pacific Ocean at the upper portions of the Pacific Plate. A lot of mid-ocean ridges, so that accounts for the really faster seismic waves that move through it. So it gives us a unique view of the interior of the Earth. Okay, then there's the Earth's magnetic field, which is very interesting. This, I think, is the last topic we'll talk about. But we have a magnetic field, and it's great because it protects us from a lot of cosmic radiation. And essentially, the reason why we have one is because we have convection in the liquid outer core, and it creates a geodynamo. Okay, and that's caused by kind of spiraling columns of electrically charged fluid in the liquid outer core. Okay, so the patterns, the convective patterns change over time. Let me just show you what this kind of looks like. Okay, so here are those spiraling motion of material in the liquid outer core, and this creates the magnetic fields in the that are generated and that move through the entire Earth. Okay, and so what it resembles is if we had like a nail that moved through a coil, and the coil was connected to a battery, that would generate the same magnetic fields that we see today. So here is the kind of magnetic north and south pole. Okay, they're not the same as a geographic north and south pole. Then here are those magnetic field lines that kind of move from the south to north pole. Okay, so it behaves much in the same way as this over here. It's like a dipolar field. Okay, so we can measure the magnetic field via looking at old minerals of magnetite that have crystallized from lava. Okay, and that kind of those magnetite grains act like a compass and point towards the north and south poles. And what we've noticed is that over time, the poles actually move and shift, and they shift significantly, especially over geologic time. Okay, so if you have, for example, magnetite grain in the northern hemisphere, it's going to point directly downwards. Okay, over here at a high latitude, it's going to point in this direction, and if you're at the equator, it's just going to point in that direction. And if you're at the South Pole, it'll point in this direction. Okay, so that's the inclination or dip of the magnetic field depending on where you are. Okay. Oops. And so this is the moving magnetic field over time. In 1904, this is where the North Pole was, and it's shifting. And this book was written in 2015. It has since moved from there. Google Maps has to update the location of the magnetic North Pole on a yearly basis because there are slight shifts. Okay, so you can see it's different from the geographic North Pole. So North Pole is moving over time. Okay, and the other crazy thing that occurs, and we've talked about this before, but there are magnetic reversals. They occur about on average, like 4,000 years. And they're just, at this point, there's no pattern that we've determined, so we just call it random. The North and South Pole switch. And it takes a few thousand years to complete, but during that time, the magnetic field that protects our Earth decreases, and it's about 10% less than normal. Okay, so we actually don't fully understand what would happen during this major shift. Okay, and this suggests that convection patterns in the outer core change over short time spans because in only a few thousand years will this change completely take place. Okay, and we talked about this when we talked about the theory of plate tectonics. That's how it's kind of like a review there. But there are some interesting connections. Okay, during the breakup of Pangaea, remember Pangaea was a supercontinent where it was one major landmass, and as it broke apart and shifted away from each other, that created a bunch of convergent plate boundaries surrounding all those landmasses and forced a lot of subduction. Okay, so a lot of cold subducted slabs started to descend to the core mantle boundary, and as this happened, those cold slabs started to displace the hot lower mantle, and that seemingly caused more mantle plume activity. Okay, and what some scientists think is that the cold slabs that made it to the core mantle boundary may have disrupted the core convection kind of cycles, okay, and the magnetic reversal activity, because we haven't seen a magnetic reversal